Hello, everybody. Welcome to join me back in the series of how you can build great solutions with the Microsoft Azure well-architected framework. Today, we are already at episode 4, meaning that we're going to have a deep dive together on the third pillar in the framework itself, which is performance efficiency. My name is Jing Liu, and I'm a cloud solution architect working in Microsoft Sweden with a partner organization. Without further ado, let's kick off. Whether you are running a public-facing application that handles massive amounts of traffic or an internal business API that manages critical data for internal systems, your users expect a system that performs well. While scaling your system to handle load, identifying the network bottlenecks, and optimizing your storage performance are important tasks to ensure that your users have the best experiences. That's why in this session, you will learn about the performance efficiency pillar of the Azure well-architected framework. Well, hope you still remember that when we were at the first session, the overview of the entire WAF framework, we talked about the different scaling mechanisms that you can utilize to meet the demand changes. In a hypothetical world where application demand was constant, it would be very easy to predict the right amount of resources you need. And to be specific, when we say resources, we could mean most commonly the memory and CPUs of the VMs. And we can also mean, for example, bandwidth or request units for the other Azure services. So basically anything that you need to support your workload to be run properly. In the real world, we know that the demands of application, they change over time. So the right amount of resources you will need can be harder to predict. If you're lucky, that change will be predictable or seasonal, but that's not always the case. So ideally, you always want to provision the right amount of resources to meet the particular demand. And to do that, scaling is a process of managing your resources to help your application meet a set of performance requirements. When you have too many resources serving your users, you won't be using those resources efficiently and you'll be wasting money. And that is what's illustrated on the first part on the diagram. However, when you have too few resources available, the performance of your application can be adversely affected. And your goal is to meet your defined performance requirements while optimizing for cost. Scaling is difficult in an on-prem scenario where you purchase and manage your own servers because adding resources can be very costly and often takes too much time to bring resources online. However, in the cloud, it is a lot easier to do thanks to the agility we get. And that's what we're going to explore further in this session. What are the different options you can do in Azure to do scaling? The first option is to do scaling up or scaling down. Basically, this is a process where you increase the capacity of a given instance. For example, to increase your processing capacity, you might increase a VM from 1 vCPU and 3.5 gigabytes of RAM to 2 vCPUs and 7 gigabytes of RAM, as illustrated on the diagram. We already talked about this last time, and so this time we can go a little bit deeper and look at what are the other scaling up and down scenarios we have in Azure other than the VMs. Another example we have is in Azure SQL Database. This is a platform as a service implementation of Microsoft SQL Server. You can scale up a database based on the number of database transaction units, also known as DTUs or vCPUs. Here, DTUs are an abstraction of underlying resources and are a blend of CPU, I/O, and memory. For example, you could scale your database in your Azure SQL database from a size of P2 with 250 DTUs up to a P4 with 500 DTUs to give the database more throughput and capacity. Another example is Azure App Service. Websites run on a virtual server farm, which is known as an app service plan in this case. You can scale the app service plan up and down between the different tiers. And you also have capacity options within those tiers. For example, an SI app service plan has one vCPU and 1.75 gigabytes of RAM per instance. And you could scale up to an S2 app service plan, which has two vCPUs and 3 gigabytes of RAM per instance. Depending on which service you're scaling, there are different considerations as well regarding downtime. For example, if you choose to scale up in Azure SQL database, the service deals with scaling up individual nodes and continues the operation of your service. Basically, behind the scene, changing the service tier or performance level of a database creates a replica of the original database at a new performance level. Connections are then switched over to the replica. No data is lost during this process. There will be a brief interruption when the service switches over to the replica, and that interruption is typically less than 4 seconds. Alternatively, if you choose to scale up or down a virtual machine, you do so by selecting a different instance size. In most cases, if the VM is already running, you are required to restart the VM. And with that in mind, expect that a reboot will be required when you scale your VMs, and you need to account for that in your planning. Finally, you should always look for places where scaling down is an option. If your application can provide adequate performance at a lower price tier, your Azure bill could be reduced as a result. You now know that scaling up and down adjusts the amount of resources a single instance has available. The other option, scaling out and in, adjusts, on the other hand, the total amount of instances. The following illustration shows the example of changing the number of virtual machine instances. Other than that, we have some additional examples as well, what scaling out or in can mean in the context of Azure resources. For the infrastructure layer, you would like to use virtual machine scale sets to automate the addition and removal of extra instances. In details, the virtual machine scale sets, they let you create and manage a group of identical and load balanced VMs, and the number of VM instances can automatically increase or decrease in response to demand or defined schedule. Another example can be found in the Azure SQL database implementation, where you could share the load across database instances by a technique called shading. Shading is a technique to distribute large amounts of identically structured data across a number of independent databases. And finally, in the Azure App Service, the App Service plan is the virtual web server farm that hosts your application. And scaling out in this context means that you are increasing the number of VMs in the farm. As with virtual machine scale sets, the number of instances can be automatically raised or lowered in response to certain metrics or schedule. Scaling out is easily performed via the Azure portal, but you can also use the command line tools or the Azure Resource Manager templates. In most cases, it's a seamless process to the end user. And autoscale is a feature that is very important to mention here. With autoscale, you no longer need to worry about scaling the services manually. Instead, you can simply set a minimum and maximum threshold of instances. You can, for example, scale based on specific metrics like queue length or CPU utilization. You also can scale based on schedules. An example is weekdays between 5 p.m. to 7 p.m. The following illustration shows how the autoscale feature manages instances to handle that load. In addition to the basic concepts, I can also take the chance to share two best practices when you are defining your autoscale schedule. The first one is to ensure the maximum and minimum values, they are different and have an adequate margins between them. For example, if you have a setting that has a minimum equals 2 and maximum also equaling to 2, and the current instance count is 2, then basically this rule is not doing anything. So it's important that you keep an adequate margin between the maximum and the minimum instance counts, which are inclusive. Autoscale always scales between these limits. Another best practice is to always use a scale out and scaling rule combination that performs an increase and decrease. If you use only one part of the combination, autoscaling will only take action in a single direction, either scaling out or scaling in, until it reaches the maximum or minimum instances. This is not optimal, as ideally you want your resource to scale up at times of high usage to ensure availability. Similarly, at times of low usage, you want your resource to scale down so you can realize cost saving. So don't forget about that. And on the last note about scaling, I also have two considerations that will be good to be aware of when you're doing scaling in and out. The first point, when you're scaling out, the start time of your application can actually impact how quickly your application can scale. For example, if your web app takes 2 minutes to start up and become available for users, that means each of your instances will take 2 minutes until they're available to your users. And you need to consider this startup time when you determine how fast you want to scale. Another point is that you also need to think about how your application can handle state. And this applies in a scenario when the application scales in. Any state that was stored on the instance that's removed from your environment will hence be lost. If a user connects to an instance that doesn't have its state, your application might actually force the user to sign in or reselect their data. The result is a poor user experience. A common pattern here is to externalize your state to another service, for example, using Azure Cache for Redis or SQL database, which makes your web servers stateless. Now that your web front ends are stateless, you don't need to worry about which individual instances are available. They're all doing the same job and are deployed in the same way. And now let's jump to a demo. I will show you how you can configure a virtual machine scale set and how you can, for example, set the auto scaling rules from there. From the Azure portal, I just created one virtual machine scale set resource. As you can see from here, I'm running the standard B1 series VM and currently it has only one instance. You can also see it if you go to the instance cap. This is the single VM instance I have from the start. And now if I go to the scaling tab, here I can set whether I want the scaling to be done manually or automatically. And in this demo, I will actually want to show you how you can configure an auto scaling mechanism. So I've already selected the custom auto scale. And down here, this is my scaling condition. I would like the scaling to be performed based on a matrix, and I have already put in place both a scale out and a scaling rule. First, let's check what I have in my scale out rule. The matrix source here, there are many sources that you can choose from. By default, you can, the easiest one to do is to monitor the CPU level of this particular VM. And if it goes, let's say, more than 70%, you can then spin up another instance. But in this demo, I actually choose to look at another metric, which is to monitor my storage queue depth. And to prepare for the demo, I have already created a queue in my storage account. So yeah, this is just a queue that allows you to add additional messages in there. And in my scale up policy, I would like it to monitor how many messages I have in my queue. So if it detects that per instance, if there's more than 5 messages in the queue, then I will actually increase the instance count by 1. So that is the main logic what the scaling policy specifies. Two additional things to call out here. The greater than 5, this is the number per instance, meaning that if you already have 2 instances of VMs in your virtual machine scale set, then you actually need to have 10 messages in order for the scale out policy to kick in. And in the other field, we have this cooldown property and currently has 5 minute set, meaning that whenever you have already scaled out, when the rule kicks in, you actually wait for 5 minutes. So even though the load might change again during that 5 minutes, you won't see another change until the cooldown period expires. And similarly, in my scaling policy, I'm also looking at exactly the same queue depth. And then the condition is that if I detect it per instance, if the message queue is lower than 2, then I will actually decrease the count by 1. And it's the same 5 minutes cooldown time. And overall, I have also specified the instance limits, minimum 1 instance, maximum 5, and default is 1. I really make sure that there are some gaps between this value. All right, so from here on, let's see if I'm adding some messages in my queue. Let me just type some. I'm just adding some messages. And currently I have 6. So according to that condition, I should have another instance created in my virtual machine skill set. If I go to instance, this should be a really fast process. As you can see now, you already see there are 2 new VM instances are being created. In fact, we only need 1, and you see 2 because this is just how the tool works, and which one ever finished first will get created, and the other will not actually become a resource later on. And if I keep refreshing, now, after about 1 minute, I see that the second instance is successfully created, and now I have 2 instances running. And now let me continue adding more messages in my queue and see what happens. And now I have created 11 messages. So according to the rule, I should have another instance being spun. But first, we need to wait for 5 minutes for the cooldown period to pass. And let's come back later to check. Now, after the cooldown period has expired, let me again refresh it. Now you see I have in total 3 instances. That's because the scale out policy identifies that, hey, you again reaches the condition and you need another instance. And now let's also test in how the scale in works. Again, going back to my queue, I will start dequeuing my messages. And now I have only 3 messages left, and let's see what happens. You see here, one VM instance is being deleted because it identifies that we have now less messages in the queue. And now I have only 2 instances left. Let me continue dequeuing the messages. And now I have only 1 left. Let's check after 5 minutes what will happen. Now, after 5 minutes, we're back to the instance portal, and let me try to click on the refresh button again. See, now even the second instance of the VM is being deleted. Keep on refreshing. And now we only have 1 instance left. The reason is that the number of queues we have in our queue depth is only 1, and that's less than the 2 per instances that we have specified in our scaling policy. So that's basically how you can utilize the auto scaling method in the virtual machine scale set to automatically control how many VMs you need in this particular scale set. And if you go to the scaling tab again, there is tab called the run history. And let me change the time to the past 1 hour. And here you can also see how the scaling actually works. We have initially 1 instance, and then it jumps to 2, and then we have 3 for a while, and then we have the 2 instances, and now we have only 1. So you can monitor how many instances, how the change has been in the past. And another place you can check is the activity log. The last activity autoscale scale down completed. If you look at the messages, you can see that the number of instances decreases from 2 to 1, and that's exactly what we saw earlier on. All right, so this is a small demo of how you can use the auto-scaling mechanism in the Azure Virtual Machine Scale Set. And next, I would like to spend a couple of minutes to talk about the technique of throttling. Basically, we have already established that the load on an application varies over time. And this variation might be because of the number of active or concurrent users and activities that are being performed. You can use auto-scaling to add capacity, but you can also use what we call a throttling mechanism to limit the number of requests from a source. In this way, you can safeguard performance limits by putting non-limits into place at the application level. Hence, you prevent the application from breaking. Throttling is most frequently used in applications that expose API endpoints. And next, I would like to share some of the common approaches how you can do throttling. The first one is rate limits. Rate limits are usually used to protect against short and intense volume bursts. For example, if you know your backend service has a bottleneck at its database with a high call volume, you could set a rate limit by key policy to not allow high call volume by using this setting. You can also use quotas. These are usually used for controlling call rates over a longer period of time. For example, they can set the total number of calls that a particular subscriber can make within a given month. For monetizing your API, quotas can also be set differently for tier-based subscriptions. For example, a basic tier subscription might be able to make no more than 10,000 calls a month, but the premium tier could go up to 1 million calls per month. And another type is IP address throttling. As you can see in the example, the following policies restrict a single client IP address to only 10 calls every minute with a total of 1 million calls and 10,000 kilobytes of bandwidth per month. And now let's temporarily leaving scaling and we'll talk about another topic, which is to optimize your network performance. Well, network performance can have a dramatic impact on the user's experience. There is a saying that slow is the new down. In complex architectures with many different services, minimizing the latency at each network hop can affect the overall performance. And some basic concept, latency is the measure of delay, and network latency is the time it takes for data to travel between a source to a destination across a network. In a traditional data center environment, latency might be minimum because the resources they often share the same location and a common set of infrastructure. However, in comparison, a cloud environment is built for scale. Cloud-hosted resources might not be in the same rack, data center, or region, and this distributed approach can have an impact on the round-trip time of your network communications. While all Asian regions are interconnected by a high-speed fiber backbone, the speed of light is still a physical limitation, and calls between the services in different physical locations will still have network latencies directly correlated to the distance between them. And then if you look at what are the places where you can have latency, usually we say that you can have latency between your Azure resources, and you can also have latency between users and Azure resources. In the next couple of slides, we'll go into each of these scenarios to look at some concrete examples and what approaches you can use to combat against those latencies. And first, let's take a look at how you can reduce latency between Azure resources. Imagine that you work for a healthcare organization that's pilot testing a new patient booking system. And this system runs on several web servers and a database. In the beginning, every component is located in the West Europe region, but later on, it is decided that the database also needs to serve users in Australia. So as a result, now the front end is being replicated also to the new region as illustrated in the diagram, but we still have only one instance of the database that is in the original West Europe region. Without any special actions, if a user that is based in Australia who needs to have access to the data, then there is this unavoidable latency between the web front end and the database layer? And what are the different ways we can use to help with that? Well, the first option is to create a read replica of the database in Australia. A read replica here allows reads to perform well, but writes still incur latency. And Azure SQL database geo-replication allows for read replicas. Another option is to sync your data between regions with Azure SQL Data Sync. A third option is to actually change the underlying technology of the database. You can use, for example, a globally distributed database such as Azure Cosmos DB. And this database will allow both reads and writes to occur regardless of location. But it might require changes to the way your application stores and references the data. And last but not least, you can also use caching technology such as Azure Cache for Redis to minimize high latency calls to remote database for frequent access data. No matter which option you go for, the goal here is to minimize the network latency between each layer of the application. How you improve your network latency depends on your application and the data architecture. Azure provides mechanisms to resolve latency issues through several services, as we have already discussed. Well, we've already looked at the latency between your Azure resources, but you should also consider the latency between your users and your cloud application. And you want to optimize delivery of the front-end user interface to your users. And let's look at some ways to improve the network performance between your users and your application. If you continue on the previous example, when a user wants to access the web front end, how can we always make sure that the user is routed to the region with lower latency? The answer is to use technology called Azure Traffic Manager. Azure Traffic Manager is a DNS-based load balancer that you can use to distribute traffic within and across your Azure regions. Rather than having the user browse to a specific instance of web front end, you can configure different mechanism on Traffic Manager to do the routing more intelligently. And the different options you can use include the first one, priority-based, meaning that you specify an ordered list of front-end instances. If the one with the highest priority is unavailable, Traffic Manager will route the user to the next available instance. Another common approach is the weighted algorithm. You basically set a weight against each front-end instance, and Traffic Manager then distribute that traffic according to those defined ratios. And lastly, you can also make the traffic balancer follow a performance-based algorithm. So basically, it will route the user to the closest front-end instance based on network latency. And now we on to another scenario. Your website most likely will use some form of static content, either whole pages or access such as images and videos. This static content can be delivered to users faster by using a content delivery network, also known as CDN, such as the Azure Content Delivery Network technology. With content deployed to Azure Content Delivery Network, those items are copied to multiple servers around the globe. Let's say one of those items is a video served from a blob storage. The team then configures the website so that each user's link to the video references the CDN edge server nearest to them, rather than referring the blob storage originally. And this approach puts content much closer to the destination, which reduces latency and improves the user experiences. The second illustration shows how using Azure Content Delivery Network puts content closer to the destination, which reduces latency and improves the user experiences. A last note to point out, content delivery networks can actually also be used to host cached dynamic content. But here, extra consideration is required though, because cached content might be out of date compared with the source. And context expiration can be controlled by setting a time to leave a TTL. If the TTL is too high, out of date content might be displayed and the cache would need to be purged. And continue on the discussion, how do you handle latency between users and Azure resources? We now consider another scenario, the hybrid case, because we know that today many customers, they still have one leg in Azure and the other leg in their on-prem infrastructure, and we need the network connectivity from on-prem to Azure. And how do you reduce the latency as a result of that? Well, for users who connect to applications, whether they're hosted on VM or on platform as a service offering like Azure App Service, you definitely want to ensure that they have the best connection to your applications. You can always use the public internet to connect users to your services, but internet performance can vary and might be affected by outside issues. Also, in some cases, you might not want to expose all of your services over the internet for security reasons. So in this case, you might want to consider using a private connection to your Azure resources. Site-to-site VPN over the internet is an option, but do know that the VPN overhead and internet variability can have a noticeable impact on network latency for high throughput architectures. To solve this issue, we can use the Azure Express Route. Express Route is a private dedicated connection between your network and Azure, and it gives you guaranteed performance and ensures that your users have the best path to all of your Azure resources. The following illustration shows how an express route circuit provides connectivity between on-prem applications and Azure resources. As a result, this ensures the lowest latency possible for the user to connect to the application. All right, so with that said, we have already concluded the part how you can optimize your network performance. And now we move on to discuss why it is important to include the storage performance considerations in your architecture as well. Just like network latency, poor performance at the storage layer can also affect your user experience very negatively. And how would you optimize your data storage? What things do you need to consider to make sure that you are not introducing storage bottlenecks into your architecture? And now let's explore some of these aspects together. Let's first take a look at how you can optimize storage for your VMs. This storage in this case plays a critical role in the performance of your VMs. Selecting the right disk type for your application is an important decision. Different applications will have different storage requirements, and that's very natural. And your application might be sensitive to, for example, latency of these recent writes, or it might require the ability to handle a large number of input and output operations per second, or greater overall disk throughput. There are four options you can choose from when you are selecting a disk. The first one is a local SSD storage. Well, each VM has a temporary disk that's backended by local SSD storage. The size of this disk varies depending on the size of the VM. Because this SSD is local to the virtual machine, the performance is very high. But data could be lost during a maintenance event or a redeployment of this VM. And this disk is only suitable for temporary storage of data that you don't need permanently. For example, this disk is great for the VM's page or swap file, and for things like tempdb in Azure SQL Server, there's no charge for this storage. It's included in the cost of the VM. Another option is the standard storage HDD. This type of storage is spindle disk storage, and it might fit well where your application isn't bound by inconsistent latency or lower levels of throughput. A dev test workload where guaranteed performance isn't required is a great candidate for this type. Then we have the standard storage SSD. This SSD-backed storage has the low latency of an SSD, but with lower levels of throughput. A non-production web server is a good use case for this type. And finally, we have the best candidate. We have the premium storage SSD. This SSD-backed storage is well suited for those workloads that are going into production and require the greatest reliability, demand consistent low latency, or need high levels of throughput and IOPS. Because these disks have greater performance and reliability capabilities, they are recommended for all production workloads. However, you also need to check that premium storage, they can only attach to a specific VM sizes. So do read the specification carefully when you choose that. So in summary for this part, whenever you rely on VM workloads, you need to evaluate the performance requirements of your application to determine the underlying storage that you should provision for your virtual machines. And now moving to the right-hand side, we're going to look at how you can optimize storage performance for your application. There are two main strategies. The first one is to use caching. A common approach to improve application performance is to integrate a caching layer between your application and your data source. A cache typically stores data in memory and allows for fast retrieval. And this data can be frequently accessed data that you specify from a database, or temporary data such as the user state. You have control over the type of data stored, how often it refreshes, and when it expires. By co-locating this cache in the same region as your application database, you reduce the overall latency between the two. And pulling data out of the cache is almost always faster than retrieving the same data from a database. So in conclusion, by using a caching layer, you can substantially improve the overall performance of your application. And this part is illustrated on the first diagram, as you can see on this slide. Another strategy to optimize storage performance for application is what we call the polyglot persistence. But essentially, it just means that you should use different data storage technologies to handle your storage requirements. Consider you have a following e-commerce example. Suppose that you store application assets in a blob storage, product reviews and recommendations in a NoSQL store, and user profile or account data in a SQL database. The second illustration shows how an application might use multiple data storage techniques to store different types of data. It's very important to note that different data stores are designed for certain use cases or might be more accessible because of cost. As an example, storing blobs in a SQL database might be costly and slower to access them directly from a blob store. Changing gears again, in today's fast-paced digital world, your users expect more from your applications, and you definitely want them to have a great experience and not be affected by performance issues. That's why we are now going to look at how you can identify potential performance bottlenecks in your architecture. The first point here is to understand what is the performance requirements that you're trying to fulfill. Before we talk about performance, it's important to talk about requirements. In theory, you could keep improving scalability and performance further and further without the end. At some point, though, more improvement is prohibitively expensive, difficult, and doesn't have enough business impact to be worthwhile. That's why it is key to agree on a set of acceptable non-functional requirements with your customers. And some examples are how fast a transaction must return under a given load, how many simultaneous connections your application needs to support before it begins to return errors, and if there's server failure, what's the maximum amount of time your application is allowed to be down before backup is online. Defining these requirements in advance of building your solution is very critical. They basically ensure that your application meets those expectations but doesn't require more effort or cost more money than necessary. The second point is performance monitoring options in Azure. Monitoring is the act of collecting and analyzing data to determine the performance, health, and availability of your business application and associated resources. You want to be kept informed that your applications are running smoothly. Proactive notifications can be used to inform about critical issues that arise, and there are many layers of monitoring to consider. Well, this might sound familiar because we actually talked rather extensively in the module of operational excellence regarding the topic of monitoring. So basically here you will have a recap. The most important tooling we have on the platform to do monitoring is Azure Monitor. Azure Monitor provides a single management point for your infrastructure level logs and monitoring for most of your Azure services. And Azure Monitor maximizes the availability and performance of applications by delivering a comprehensive solution for collecting, analyzing, and acting on telemetry from your cloud and on-prem environments. As you can see in the diagram, it depicts a high-level view of Azure Monitor. At the center of the diagram are the data stores for metrics and logs, and these are the two fundamental types of data that Azure Monitor uses. On the left side are the sources of monitoring data that populate these data stores. On the right side are the different functions that Azure Monitor performs with this collected data, such as analysis, alerting, and streaming to external systems. And finally, I also want to share some words about log analytics. Centralized logging is a very efficient strategy to help you uncover hidden issues that might be difficult to track down. With log analytics, you can query and aggregate data across different logs. And this cross-source correlation can help you identify issues or performance problems that might not be evident when you look at logs or metrics individually. You can collect a wide range of data sources, security logs, Azure activity logs, and server, network, and application logs. In addition, you can also push on-prem System Center Operations Manager data to log analytics in hybrid deployment scenarios. Then Azure SQL database can send diagnosis information directly into log analytics as well for detailed performance and monitoring. And now again, we are at the end of the session, and here's the summary of what we talked about, what you can do to improve performance efficiency as described in the well-architected framework. In this session, we started by looking at various options for scaling your application and how to use auto-scaling to handle scaling automatically. We've also looked at different ways to optimize network traffic for your application. You've seen how you can use services like Azure Traffic Manager to direct users to the closest application instance. And you've also learned how caching content on Azure Content Delivery Network can improve performance. Then we moved on and looked at how you can optimize the storage performance of your application. Selecting the proper storage tier has a direct impact on performance, and using caching services such as Azure Cache for Redis will help improve throughput for data access. And finally, you've learned and reviewed about ways to identify performance bottlenecks in your application. Using tools such as Azure Monitor and Application Insights can provide valuable performance insight in your application. And this tool can help you deliver a great experience for your user. As usual, I found some resources that you can read more closely into to understand, for example, how Azure Virtual Machine Scale Sets work, some of the additional best practices for using auto scaling. If you want to know more throttling strategies, here's a link for you. And then we also have some more deep dive links if you want to learn more about Azure Cache for Redis, what is Content Delivery Network, how Azure Traffic Manager works, and all you need to know about Azure Monitor. So hope you find these resources useful. And now at the very last page, we have again the Q&A corner. Today, I prepared two common questions related to virtual machine scale set. The first question is, if I reduce my scale set capacity, let's say from 20 to 15, for example, which VMs are removed? By default, VMs are removed from the scale set evenly across fault domains to maximize availability. And VMs with the highest IDs are removed first. You can basically change the order of virtual machine removal by specifying a scale-in policy for the scale set. And another common question, we know that it's a common confusion actually, what's the difference between availability set and virtual machine scale set? An availability set consists of a set of discrete VMs which have their own names and individual properties, but are spread across 4 domains, which means when you have more than one VM in a set, it reduces the chances of losing all your VMs in event of a hardware failure in a host or rack. The purpose is to address reliability. And we're going to talk more about availability sets in the next session. On the other hand, a scale set consists of the set of identically configured VMs, also spread across 4 domains. And in fact, a scale set is actually an implicit availability set with 5 4 domains. The main difference is scale sets being identical make it very easy to add and remove VMs from the set while preserving high availability, which in turn makes it easy to implement autoscale and to perform operations on the whole set or a subset of VMs. The main purpose is to address scalability, fulfilling the changing demands of resources. So you can say that the availability set and the scale set, they actually have different purposes. All right, so hope you enjoyed today's session. And next time, we're going to explore together the reliability pillar in the well-architected framework. Stay tuned and see you soon.